So many times what happens that you need to find a big problem, and what you can do is you can find that the answer of the bigger problem by breaking it down into smaller sub problems, right? So if you break it down into smaller sub problems and find the answer of each of the sub problems and somehow combine it to find the answer of the bigger sub problem. So but then what is the difference between dynamic programming and recursion? In dynamic programming, what happens is that once we calculate the smallest subproblem's answer, we somehow store it. So like we store it in the sense that when we require it again, then we don't need to recalculate the entire subproblem again from scratch. We already know that we have already calculated it beforehand and the answer is this. So we can take the answer and calculate to find the answer of the bigger subproblem. Whereas in recursion, we don't take care of any storing or something. We just blindly, whenever we want to calculate the smaller subproblem, we again calculate again from scratch. So this was the idea, the flavor of dynamic programming. Let's move on to a prime example of dynamic programming. So this is the problem statement. This says that there are n stairs in front of you. You need to climb up the stairs in such a way that you can either take one step or you take two steps at a time. What are the total number of ways of climbing the stairs? So there's an image here to represent this problem statement. Say the bottommost step, say the step is number is 0, and here total 1, 2, 3, 4, 5 steps, right? So these are these are some of the ways which is shown that in which you can climb the nth step. So here you can take one step at a time to reach the fifth step. Here you can see that you are taking two steps and then again two steps, then again one step. Then here taking one, then two, and then one. Here you can take one, and then direct two to reach the fifth step. These are only four ways shown. Like there are many other ways. So for a given general n, it is asked that what are the total number of ways of climbing the stairs. So anyone like here in the meet has an idea of how to approach this problem? You can unmute and speak.
We have to solve for two cases when n equal to even and n equal to odd. So when n equal to even, then we will do it n equal take step
N equals to even.
Yeah, n equal to even and n equal to odd.
No, the thing is that you can climb up either one step or two steps at a time. So how even comes here?
Like if suppose there are three steps, for example, when n equal to 3. So there are one possible way is first I take two steps and then I can take only one step. I cannot take two other steps. And then if suppose n equal to 4 steps, when it's even, we can all the steps can be taken when n equal to even, then we can take two steps for all these steps. But if n equal to odd, then there must be at least one step where we have to take one step.
Okay, I think you're misunderstanding the problem. I'm asking what are the total number of ways of climbing the stairs. I'm not asking the minimum number of ways. Are you understanding the minimum number of ways? Like minimum number of steps to climb the stairs?
No, like I was solving for two different cases and trying to add those.
Okay, so like for 3, you're saying you can take one, like you can take 2 and then 1, right? Hello?
Yeah, no, what I was saying is that if there are even number of steps, then all the process can be taken by two steps. Like I can climb it 2, 4, 6, 8, 9, like that. But if it is even odd number of steps, then we have to take even and then final step must be odd, or the first step must be odd and the rest can be. So we have to solve for two different methods, n equal to even, n equal to odd, and then add the
No, but
pieces.
these are not the only cases, right?
Yeah.
Like okay, your idea is correct, but I think the notion of even and odd is incorrect. Like the first step, like you can take the first step to be only one step, and then remaining n-1 step, you can find the answer later on, right? Or you can take a 2-step and then you can find the answer of n-2 later. Is that what you're trying to say?
Yes.
Okay, yeah, then it's fine. But it's not related to even or odd. Okay. Yeah, so yeah, it's correct. So basically what we're trying to do is like say yes, yeah. So what is happening here is I have to climb n steps, right? So how I can climb n steps? There are two possibilities. I can either like this is the n step. I can reach the n step by taking only one jump, like one jump. Then if I take one jump to reach this step, I was previously, that means I was previously at n-1, right? So say f of n is the answer of for number of ways to reach n step. So this f of n is equal to f of n-1. So the number of ways I can reach n-1 plus if I reach this n step by taking a jump of 2, then that means that I was previously at n-2, right? I was previously at n-2. And in how many ways I can reach to n-2? I can reach n-2. I can reach f in f of n-2, exactly. Yeah. So the number of ways I can reach f of like n step, f of n, is the number of ways I can reach n-1 steps, f of n-1, plus the number of ways I can reach n-2 step, which is f of n-2. So this is the recursive relation for f of n. So this recursive relation is kind of very famous. Can anyone like say which relation is this? Which sequence is this?
Fibonacci sequence.
Yeah, exactly. This is the Fibonacci series. So this is the Fibonacci series. So like f of n is the Fibonacci, like the number of ways you can reach the nth step is the nth Fibonacci number, where the base cases are what? F of 0 is 1 and f of 1 is also 1. Like in the 0 step, you are not moving at all, so there's only one way to be there. And f of 1, you can only take one jump to reach there. Yeah, I like please bear with my handwriting, is kind of awful, I know, but yeah, I hope you're understanding it. So yeah, this was pretty much about the logic of the problem. Now let's move to the coding part. So yeah. So this is the naive move of naive code, which is using recursion. So it says if you're taking this function moves, which takes an integer n. So if n is 0, if n is 1, then I'm just returning 1, which is basically the base case here. F of 0 is 1 and f of 1 is 1. Else you're returning moves of n-1 plus moves of n-2. So basically this recursive call, like f of n is f of n-1 plus f of n-2. This is the code. This uses recursion, but actually this code is quite inefficient. Let's see why. So this is the call tree of this particular function. So like let's say someone asks me to find the number of ways to reach fifth step, like f of 5. So fib of 5, if I see if fib of 5 will call what? Fib of 5 will call fib of 4 plus fib of 3, right? Because like n is f of n is an f of n-1 plus f of n-2. So it will call fib of 4 and fib of 3. Fib of 4 will call again fib of 3 and fib of 2. Fib of 3 will call fib of 2 and fib of 1. Fib of 2 will call fib of 1 and fib of 0. These two are base cases, like we have already defined it to be equal to 1. So yeah, so we don't go any further below. We add them up to get fib of 2. Now fib of 1 is also defined. We add them up to get fib of 3 and so on. We again move up, right? So let's see here, let's say take this fib of 2. When this fib of 2 is called with fib of 4, we again go down and call fib of 1, fib of 0, and then add it up and to get fib of 2. Then again we have calculated fib of 4 completely, then we move to fib of 3, and then fib of 3 again calls fib of 2. But we have already calculated fib of 2 here by adding fib of 1 and fib of 0. But if we, according to this code, this doesn't know this fact that we already calculated fib of 2. This fib of 2 will be again completely calculated from scratch by breaking down into fib of 1 and fib of 0, adding them up and again calculating fib of 2 and then again adding these two up to get fib of 3. So this is an inefficiency of this code. So due to this fact, the time complexity of this code is exponential. So if you call for n, so it will take time of order of 2 power n. So yeah. So let's see how dynamic programming saves a life by optimizing this code. Yeah, this is the optimized approach. There are two methods of optimizing it. Let's see the first approach. I'm just storing and defining an array of size, DP of size like 1e5, and then this is my optimized code. It says if n is 0, n is 1, then return 1. This is the base case. And I am, as you see the comment, I'm saying that assuming that line initialized all the elements of DP to -1, right? So the initialized value is -1. So if DP of n is not equal to -1, then I return DPN. Else I'm returning DPN equals to move some n-1 plus move some n-2. So what does it say? This particular thing says that DP of n is not equal to -1. It means that it's not -1, it means it's something else. And when does it become something else? When does it get updated? It gets updated only in this line, right? DP of n is moves n-1 plus moves n-2. This particular if part means that DP of n is already calculated beforehand. This particular part means that if DP of n is already calculated for you, then you don't need to go to this next line, like move of n-1 plus move n-1. You can directly return DP of n. So, but if it is not calculated, then that means if DP of n is -1, then we have to calculate move of n-1 plus move n-2 and store this value in DP of n, so that whenever later on you calculate for DP of n, it will go to this if part, which is not equal to -1. That means it already calculated for you, and hence it will return DP of n instead of calling moves n-1 plus moves n-2. Does anybody have any doubt here? So here in this call tree, I'm calling fib of 5. This fib of 5 will call fib of 4. Fib of 4 will call fib of 3 and then calculate again. Fib of 2 I calculate again, right? To find fib of 4. Now when it goes to fib of 3, if it will see like here fib of 3, here fib of 3 is already calculated, right? It is already calculated for you. So this like DP of 3 will not be equal to -1. It will be something else. It will be like third Fibonacci number. It will not be -1. So in this code, when you again go to fib of 3, try to find fib of 3, it will see DP of 3 is not equal to -1, right? It is already calculated. So it will directly return the value of fib of third Fibonacci number. So this part is what actually is what is like storing the smaller subproblems. Like, so this fib of 5 we are breaking into smaller subproblems, but once we're calculating it, we're already storing it in an array or something, so that when it's again required later on, we don't need to recalculate again from scratch. We are just taking the value directly from the array. Does anybody has any doubt in this portion? Okay, cool. So this part is called memoization approach. This is also called the top-down approach of dynamic programming. Why it's called top-down approach? Because like it's like basically we are trying to break it down into smaller subproblems and trying to calculate the smaller subproblems and join them somehow to form the bigger problem, but without recalculating the repeated part again and again. We are kind of storing the smaller subproblems in an array so that when it's again required, then we don't need to recalculate it again. So this is the memoization approach or the top-down approach. Top-down, why? Because like we are going from top to bottom, right? We are wanting 5, we are breaking to 4 and 3, and from top we are going to down, right? So this is the top-down approach. The second approach is what is called the bottom-up approach or the tabulation approach. let's see what it says. We are inputting n, and like we are just initializing a DP of array size n plus 1. And this line means that we are initializing all the elements of the DP array to 0. And then this is our base case. So because fib of 0 is 1 and fib of 1 is 1. And from once we are done with the 0th and the first element, for I equals to 2, I less than and I plus plus, dp of I is what? dp of I minus 1 plus dp of I minus 2. This is the basically the recursive relation which we know of the Fibonacci series. And once we have tabulated, like we have like stored all the elements from I equals to 0 to I equals to n, we can just print the nth value of the array, which is the nth Fibonacci number. So what does this particular code do? This particular code is like, an n, the want to find the nth Fibonacci number. You say like, no, I won't go from top to down. Like I'll completely I'll create an array of size n, and I'll store all possible Fibonacci series, like all possible Fibonacci numbers. I'll store it from bottom. From below I'll store, like you are storing 0 and 1 beforehand. From 2 to n you are filling up the entire DP array. You are filling up the entire Fibonacci series, right? You are filling up the entire Fibonacci series using this recursive relation. Now, after this for loop, you have each and every Fibonacci number. Like you have each and every Fibonacci number from 0 to n, right? You have all the Fibonacci number. Now, you are required to find the nth Fibonacci number. You just print the nth value. So you're just putting the dp of n, right? So this method is called bottom-up approach, because as you can see, like you're tabulating the entire array from bottom, not from top. Here you are like making use of, you're breaking n into n minus 1 and n minus 2, and then you are like calculating for n minus 1, then calculating into for n minus 2, and then adding it up to form n. Here you are from below, the smaller subproblems, you're adding them up and you form the bigger subproblem, and you're filling each and every element, and then you're printing the nth element of the DP. Is there any doubt in this part? Has everybody understood the difference between the top-down approach and bottom-up approach? Like bottom approach is also called the tabulation approach, because you're tabulating, you're filling up the entire array for all the possible values of DP. Is there any doubt? Okay, cool. I hope you guys understood. So yeah, let's move on to the next problem, which is the grid problem. This also DP problem on DP. So the problem statement says that there is an n cross m grid. You are currently at the position 0, 0. You are currently at the top left corner. From here, you are supposed to reach n minus 1, n minus 1. That is the bottom right cell you have to reach. But some of the cells have obstacles. There's a typo here, okay. Some of the cells have obstacles. You cannot go to a cell which has an obstacle. Okay, so how many ways are there to reach the bottom right cell, given that you can only move down and right? So in this example, you can see you are currently here, and you have to reach the bottom right most cell. You can only move either right, or you can either move down. So using only moving down and right like this, but you cannot jump into a cell which has an obstacle. So you can only move to the free cells by moving only the free cells and reaching the bottom rightmost cell. How many ways are there to reach this bottom rightmost cell? And assume that the 0, 0 cell doesn't have an obstacle. Yeah, like the one you are currently standing on doesn't have an obstacle. Yeah, so you can take time, or like if anybody has any if you have an approach to this problem, you can speak up. I'll give you like 20 to 30 seconds or 1 minute. Anyone? Okay, cool. So I'll explain the problem, like explain the approach to this problem. So so there's a grid of n cross m. So let's say 4 cross 3. So this is a grid of 4 cross 3. Say like this and like this. These are the obstacles. So you cannot go here. You can only move in the right or in the downward direction. So let's consider a particular cell I comma j. Let's consider a particular cell I comma j. So let us consider let us define a dp 2d dp. It will be a 2d dp of where dp of I comma j is what? dp I comma j will represent the number of ways to reach I comma j cell from this 0 comma 0 cell. Understood? So like dp of I comma j will represent a number of ways you can reach I comma j itself from 0 comma 0 cell. So finally what we want? Finally want the number of ways to reach 0 comma 0 to n minus 1 comma n minus 1. That means we want to answer of dp of n minus 1 m minus 1. So this is the final answer we want, dp n minus 1 m minus 1. Let's see how we can calculate for a general I comma j. So this I comma j, how can we can reach? First of all, we need to see if it's a obstacle or free, right? So if it's an obstacle, like say like all these circled ones, if it's an obstacle like these circled ones, then dp of I comma j is 0, right? We cannot reach the cell at all because it's prohibited to reach hop into a cell which has an obstacle. So if it's an obstacle, then dp of I comma j is 0. We cannot reach it in any ways. If it is not 0, then dp of I comma j is what? dp of I comma j, then since we already said that we can move either in the right or down direction. So what are the possible cells from where we can reach this I comma j? Can anyone tell?
dp of I minus 1 comma j plus dp of I comma j minus 1.
Exactly, yeah. So this is I comma j minus 1, right? This is I comma j minus 1 cell. And this is I minus 1 comma j cell. So these are the two cells from where you can reach this, right? Because we can move only in the right or in the down direction. So from here we can move right, or from here we can move down. From no other cell we can move to this cell. We cannot move from here to here because like we have to move a left direction at least once. Or we cannot move from here because we have to move up. We cannot move from here to here. We can only cells we come from where we can reach this I comma j is I comma j minus 1 and I minus 1 comma j. Understood? So the number of ways from in which we can reach I comma j is a number of ways in which you can reach I minus 1 comma j plus the number of ways you can reach I comma j minus 1. Right. Understood. So the number of ways in which you can reach I minus this left cell plus the number of ways you can reach this top cell, add them up is the total number of ways you can reach this I comma j cell. I hope you understand. So this
We can
yeah.
Can we jump over the obstacles, like take 2 steps at a time? So like
No,
we jump
no,
from
no, no,
zero.
no, 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 no. Or you could say from here directly to here, you say.
Yeah, because how else will we reach that cell in the first place if we are only allowed to go right and down?
You can go down, right?
Yeah,
But you cannot
but
go
like
right.
yeah, so like there will be some cells which are not obstacles themselves, but we won't be able to reach those cells ever because you can
Yeah,
only go right.
yeah, we cannot like you are saying this cell we cannot reach at all, right? Yeah, you're correct.
Yeah.
You're correct. You're correct. So that for this dp of I dp of like whatever this cell is, dp of 0 comma 2 is actually 0. You cannot reach this cell at all.
Okay.
So when you calculate this dp of I comma j, it will be something this, something this. This will be 0. You cannot reach this cell from this above top cell. There are 0 ways in which you can, because you cannot reach at this at all. So you cannot reach this from here. From here you cannot reach. Understood what I've said?
Yeah.
Cool. So it can happen that the final answer is 0, like dp of n minus 1 m minus 1 0. You cannot reach the bottom right cell at all. So yeah, like that. So yeah, I hope you understood. So this is the required reconciliation. There are two cases. If it is an obstacle, then directly you can put 0 for it, or else dp of I minus 1 j plus dp of I comma j minus 1. But there are some special cases for the, let me switch colors, for the leftmost column and the topmost row, because for these cells there is nothing on top of it, and for this leftmost column there is nothing on the left of it, right? So for these, if I equals to 0, then I minus 1 doesn't make sense. Similarly, if j equal to 0, then j minus 1 doesn't make sense, right? So we need to take care for these special cases for the leftmost column, the rightmost, topmost row. Yeah. So this was the logic. Anyone has doubt in the logic? Okay, cool. So let's move to the code. Yeah, so logic is same as I said. We can see that we are at position I comma j such that I comma j has an obstacle, then we can't reach there. If there is no obstacle at I comma j, then we can reach I comma j from top or from the left. Hence the state transition is as follows. It's just as I said. If the cell is free, then dpi comma j is dpi minus 1j plus dpi j minus 1. Else dp of I comma j is 0. Yeah, this is the code of the problem. So in dp, yeah, it's not d, it's dp, dp and m is 0. So like 0 stands for obstacle and 1 stands for free cell. So yeah, dp00 is, this is the base case. Dp of 0 comma 0 is 1, because like we can only, this one way we can move to the starting position by not moving at all. And this is the for loop where for I equals to 0 I less than n, j equals to 0 j less than m. If this is the starting position, if we are at 0 comma 0, then continue. We have already calculated to be 1, and we're initializing it currently to 0. If it is an obstacle, continue, because we are already initialized it to be 0. So dp of I comma j will be 0. Else, if I not equal to 0, if I not equal to 0, then dp of I comma j plus equals to dp of I minus 1 comma j, right? If j not equal to 0, then dpi comma j plus equals to dpi j minus 1. We only add this if j not equal to 0, like if j is greater than 0. If j equal to 0, we don't need to add this because it doesn't make sense at all. And similarly, if I not equal to 0, then only we'll add I minus 1 comma j. Like this transition, I've broken into 2 steps. I'm first adding this part. Then only I'm adding this part only if I is positive, and I'm adding this part only if j is positive. I hope that this part of code is clear. If anyone wants, I can re-explain. M array is basically saying which of the cells is free or which of the cells is empty. 0 means obstacle and 1 means empty. Is it clear to everyone? The code? Okay, quick question. Is this top down or bottom up? And small reason. Why do you think so?
Top down.
Why?
Like because first we are calculating from for 0 comma 0, then we are like simultaneously moving like right or down as we see the obstacles, like as per the obstacles.
No, we are not seeing as per the obstacles, right? Like we are calculating for all possible I comma j, right? I'm moving through all I comma j, and I'm calculating for each I comma j the number of possible paths, right?
Yes.
So like I'm not starting from, it's not like I'm starting dp of n comma m, then I'm seeing, oh, n comma m will be calculated from n minus 1 comma n and n comma n minus 1. Now calculate for n m minus 1 and n minus 1 m separately and then add them up to get this. I'm not doing that, right? I'm starting from the initial base position, and from there I'm iterating to entire grid till I get to that rightmost cell, and then I'm printing dp of n minus 1 comma n minus 1. Did you get it?
Yes, got it.
Yeah, so it's bottom, it's bottom up, not top down. Anyone else has any doubt why is bottom up and not top down? I hope it's clear. Okay, cool. So yeah, so this was the code. I hope everyone understood this code. So let's move on to the next problem. Yeah, this is the dice problem. The problem statement is just a second. Yeah, the problem statement says that there is a dice having numbers 1 to 6 on it, and tell the number of ways that we can get a sum equals n on rolling the dice. Like you're given an n, you're asked to find in how many ways you can get sum of n. Like there is no restriction on the number of rolls. So let me give an example for this. Like if you're given the number 3, if you're given the number 3, you can get the number 3 in how many ways? You can directly throw a 3, or you can throw 1 then 1 then 1, or you can throw a 2 and then a 1, or you can throw a 1 and then a 2. So this, yeah, you can get an out total sum of 3 in this 4 steps. Directly 3, 1 1 1, 2 then 1, or 1 or 2, 1 then 2. These last two will be counted as different. So in this way, if you are given a general n, how many ways you can get n? So anyone has any idea? Use dp. Yeah, it's a dp session, so yeah, we use dp. Anyone?
Will it be like f of n minus 1 plus f of n minus 2 plus f of n minus 3 till f of n minus 6?
Exactly. Yeah, exactly correct. So yeah, I'll explain it. So yeah, we can see that each move, like how we can get n. Like suppose we get n like x throw, we got some n, right? We got some n. How we can get n? We can get n in first case is that we throw and we get a 1 and to get the sum n. If we get a 1, that means previously we had sum of n minus 1, right? We had sum of n minus 1. If we throw a 1 to get n. Suppose if the last throw is 2 to get n, that means previously we had n minus 2, right? And continuing like that, say if the last throw was 6 for me, that means previously I had sum of n minus 6, right? So this is 1. Yeah, this is 1. Yeah. So this is the 6 cases. So the number of ways I can get n, say f of n, is it's the sum of all these possibilities, right? Like either the last row can be 1, or the last row can be 2, or so on. The last row can be 6. So I need to add all these possibilities. So the number of ways I can get n, which is f of n, is the number of ways I can get n minus 1, which is f of n minus 1, plus the number of ways I can get n minus 2, which is f of n minus 2, so on. There is the number of ways I can get n minus 6, which is f of n minus 6, and add all these up to get f of n, right? This is the recurrence relation. F of n is f of n minus 1 plus f of n minus 2 plus so on till f of n minus 6, because there are like 6 numbers in the line. Yeah, till f of n minus 6. Does anyone have any doubt in how the logic, like how I'm adding all the possibilities?
What is f of 2?
What is f of
2.
what is f of 2? Yeah, that's a good question. So this works for a general n, but for small numbers, say f of 2, the last number, the last row can be 1, for which it will be f of 1, or the last row can be 2, which is then f of 0. That's it, right? Like I cannot get a sum of 2 by throwing the last row can be by the last to be 3. Like if I last row is 3, then I can't get a sum of 2, right? So this, all those further case won't be calculated at all. I will only stop till 2. So I need to take care of these cases for less than 6, because for less than 6, some of these possibilities which will get like f of something negative. So I need to take care of that. So did you understand? Who's over asked f of 2?
Yeah,
I think that
understood.
was only your doubt. I think that was only your doubt, like f of n minus 2 minus 6 won't hold. Yeah. So yeah, this was the special cases. Like in the previous problem, right? We had the leftmost column and the topmost row. Those were the special cases. Similarly, here we have 1, 2, 3, 4, 5, 6, all these 6 to be special cases. And for the greater than 6, we can write this general recurrence relation. And the base case is, as usual, f of 0 is 1. Yeah, so this is it. Like let's read, like hence the way to get n is basically getting a 1 at n minus 1, 2 at n minus 2, and getting a 6 at n minus 6. Hence the state transition is as follows: dp of n is n minus 1 sum till n minus 6. Yeah, just check if the integers don't go out of the bounds. Yeah, this is the demo code. It says we create a dp of n plus 1, and we initialize base case dp of 0 to be 1, and we run the for loop I equals to 1 to n. For each I, what I'm doing, I'm calculating all, like I'm iterating from 1 to 6, right? J equals to 1 to 6. For j equals to 1 to 6, for these 6, I'm adding this up and adding up to dp of n. But when will I add? I'm only add if I minus j is 0. Like currently for I, if I minus j is positive, then only I'll add dp of I minus j to dp of I, or else I won't add. So once I from 1 to 6 I've added all dp of I minus j to dp of I, I'll get this thing n minus 1, n minus 2, n minus 3 till n minus 6. And after that dp of I will be calculated, and this I will run from 1 to n. So at the end I will have all the dp values from 1 to n. So again, can anyone tell, like if it's top down or bottom up? I'm storing all the values of dp of I here, all the possible dp from I 1 to n. So is it top down or bottom up?
Bottom.
Yeah, it's bottom up again. It's bottom up because we are starting from the bottom, starting from 1 to n and storing all the possible values in dp. Yeah, cool. So anyone has any doubt in the code or any difficulty in any understanding any logic or any code, or anyone has any suggestion, anything? Okay, cool. So like these three problems like are the very standard and very standard prime examples of showing why DP is considered better and efficient instead of recursion. So yeah, moving on, we'll start with a new topic, which is Knapsack. It's a completely dynamic programming based problem, and I'll hand over to Ashish, who will take up from this part. Knapsack. Ashish, you can take over.
Yeah. Okay, just a minute. Can you see my slide?
Yeah, you are audible, visible, slides are
Okay.
visible.
Yep. So let's start with the knapsack intro. So what is basically the knapsack problem? So the knapsack problem is we have been given a couple of items, and the problem deals with the idea of taking an item or not. So we consider all the possible sub problems of a particular problem where we have to choose a particular item, or we do not have to choose a particular item. So let's see an example. So a thief has entered your house and that has n items, and the cost of each item and the weight of each item is mentioned. So the thief has a bag that can carry at most weight W. So what is the maximum amount that the thief can loot from your house? So note that we can just take one item once, like since there are not multiple copies of the same item. So if I just steal this mobile phone, I can steal this mobile phone once. Like there are not infinite copies of this mobile phone. So what can be a possible approach for solving this problem? So does anyone of you have any idea of how to solve this problem? Any hints, any suggestions? Okay, so basically, what happens is, since you can either take the item or you cannot take the item, so you have two choices, like you either take the item or you do not take the item. But what if there was an option that you can basically divide the items as into whatever weight you like. So suppose I say that I rob a general store and I have like items like wheat, rice, and some other salt and sugar. So what I can basically do in that case is I can divide the items. Like I have 100 kgs of sugar, I have 100 kgs of wheat, and the price of wheat is this, the price of sugar is this, and I have a bag like this which can carry at most, like let's say 250 kg of item. Okay, so what I'll do is I'll choose a greedy approach. है So what I'll do is I'll choose the item that is most costly per kg, because I want to fill my bag in the most efficient way. So what I'll do is I'll take the most costliest item and fill it in the bag, and take the next item, fill it in the bag, and suppose the bag reaches a capacity of 200 kgs and still there is 50 kg left. So what I can do is I can take the other item, like the half of the other item. That is, I'll take 50 kg of the other item and I'll ignore the other 50 kg and take this item into my bag. So this is a greedy strategy. It works for the case when you can partition the items into any weight that you like. But what if the items cannot be partitioned? So in that case, you cannot follow this greedy strategy. For example, like if you try taking this example, so let's say I have a bag that has a weight of 10 kgs and I have weights 5. Like my weight is 5, my weight is 4. Like I have items, this is the weight, this is the value. So I have items of weight 5, items of weight 4 that have a value of 5 and that has a value of 4. And I have 5 items of weight 2 and value 2 each. So in this case, what happens is if I follow a greedy strategy, what I'll do is I'll first take the item that weighs 5 kg and then I'll take the item that weighs 4 kg. So at the end, I'll have my bag filled up with 9 kgs and I'll have a value of 9 rupees, let's say. So in this case, this is the maximum possible value that I can achieve, because my bag cannot accommodate this item anymore and I cannot break this item any down. So my maximum possible answer in that case would be 9 rupees. But what if I choose a better strategy? So in this case, what if I decide to take all these 5 items? So in that case, I can fill my bag completely with 10 kgs and I'll get 10 rupees for the profit that I can have. So we see that the greedy strategy doesn't work in this case. So we have to come up with some different strategy that explores all the possible solutions. So like, do you like still anybody wants to suggest any strategy? Like what can we do for each of the item? So let's suppose like I have 5 items. Let's name it 1, 2, 3, 4, and 5. So what I have to do is basically I have to exhaust all the possible strategies, because I see that the greedy strategy doesn't work and there is no possible strategy in general. So the only possible option that is left for me is to try out all the possible strategies. Let's say I have 5 items. So I have to decide whether I have to take this item or not. So if I don't take this item, I say that I'm not taking this item, so I mark it as 0. Otherwise, I mark it as 1. So similarly for the other items, I have two possible choices, whether I want to take this item or I do not want to take this item. So since this completes all the possible solutions that I can have, like there cannot be any more solutions to this. Like I'm considering for all the 5 items a choice that I want to include this item in my knapsack, or I do not want to include this item in my knapsack. So I'm completing a exhaustive search on all the possible subspaces. But the problem with this is since like I have, let's say I have n items, for in that case, I will have to check for 2 to the power n combinations. So for each of the item, I'll have two choices. So if I have n items, I'll have to check for 2 to the power n possibilities. But this is kind of too costly for me to evaluate. Like this is an exponential solution, and you cannot even find the answer for n, let's say n equal to 100 in your lifetime. So the time complexity is too large for a large for to calculate for a larger value of n. So what we do is we try to think that what is the problem with this strategy. So the solution is obviously dynamic programming, because we are having a session on dynamic programming. But the condition for dynamic programming to apply is we should have a sub problem that is kind of repeating. So we saw in the Fibonacci sequence that we were calculating the Fibonacci answers for this 543. And what we saw is that when we were calculating this Fibonacci sequence, the answer for 3 was getting calculated twice. So we were kind of storing this answer, and we said, okay, let's fine, we'll store this answer, and whenever we encounter the same problem again, we will like just pick up the answer that we have stored and do not recalculate the answer. So do we see any similar structure in this case? So let's see the issue. Okay, so let's say that these are the 5 items and I have the same problem. Like this is the weight of the item and this is the value of the item itself. So let's say the item 1 has weight 1 and a value of 1 rupee. The item 2 has weight 2 and a value of 1 rupee. And similarly for the other items, like the item number 5 has weight 5 and a value of 5 rupee. So what I try to see is that, let's say I have perform my search on item number 1 and item number 2. So I have said ki I'm gonna take my item number 1, okay, and I'm gonna take my item number 2, and the total possible weight that I can take is 10 kgs. So, and I'm saying that I'm not gonna take item number 3. I'm not gonna take item number 3. So what happens is that I have said, okay, I'm gonna take item number 1, I'm gonna take item number 2, I'm not gonna take item number 3, and item number 4 and 5 I'm yet to decide on. So I'm yet to decide on item number 4 and 5, and the weight that I have left is 7 kgs, because I have exhausted 3 kgs of weight over this these two items. So the weight I'm left with is 7 kgs, and I have to yet decide on the item number 4 and 5. So this is one possible case. What I can see is that there can be other case when I can reach the same sub problem again. So let's say I say that I'm not taking item number 1, I'm not taking item number 2 either, but I have decided to take item number 3, and I'm still left with item number 4 and 5, and I have yet to decide on item number 4 and 5. So the weight of the maximum weight allowed is still 7 kgs, and I'm still left with 4 and 5. So I see that there is a sub problem that is getting repeated, and there can be multiple sub problems that can be that will be repeated in this case. So if you draw the diagram for this, like the tree diagram for this, so it will be quite complicated to draw, but you can understand from a simple example. In this case also I was left with item number 4 and 5, and the maximum possible weight that was allowed to me was 7 kgs, and in this case also I am left with the item number 4 and 5, and the maximum possible weight that I'm allowed is 7 kgs. So I need not recalculate the answer for this case 4, 5 and 7 kgs again. I can just take the answer from the previous step and store it down somewhere. So this is the idea of dynamic programming. So what we do is basically we start from the first item, and we say, like, let's say my total capacity of my bag is 100 kgs. So what happens is that I'll do a solution which says that my bag still has a capacity of 100 kgs. I am starting to choose on the item number 0. So what happens if I take this item? So if I take this item down, so I'll be reduced to a sub problem that has the, like, this is the 0th item. I'm following a 0 based indexing. So what happens in this case is the weight of my bag will reduce by the weight of the item 0, and my value will be increased by some amount, that is the value of the item 0. And I'll have to solve this sub problem where the weight of my bag actually reduces, like the maximum possible capacity of the bag reduces. I'm left with a sub problem where I cannot choose the ith item again, and I have to decide on the possible states from the first item to the other items as well. So this is a sub problem, and what we can do is we can recursively solve the subproblem, and we can store the answer for each of the cases. So this is the idea of dynamic programming. So we can see that at each state, what we can do is, what is the DP state in this case? So DP state is the state that defines your subproblem. So in this case, what made me define that this problem is getting repeated? So in this case, I was told that the weight of the bag that I can carry is 7 kgs. The remaining weight of the bag is 7 kgs, and the remaining items are 4 and 5. So the remaining items and the remaining weight actually determines the subproblem that I'm solving. So these are the two states that I need to determine what is the, like, have I encountered this problem before or not. So this is what we store in this DP state. So as in each state, we need the index that we are at, like which all items have already been chosen and which are the remaining items, and we need the remaining weight of the bag. And these two states we can store in the DP array. We can store an array of 2 dimensions, like which will store the weight, the remaining weight, and the remaining number of items. So the main idea is to see that we can either take an element or not, and if we take an element, the weight of the bag increases, and if we leave the element, the weight of the bag actually remains the same. So like, let's say in this subproblem, I said if I do not decide to take the ith item, what happens is the weight of the bag remains the same, but the I am still to decide on the remaining items, but I have decided that I will not choose the ith item in this case. So this is the sub problem, and let's see how do we define the sub problem. So let's say I'm defining a sub problem as dpij. So dpi says that I have already considered the items up till index of I minus 1, and j says that the current maximum weight that the bag can carry is j kgs. So if I decide to take the ith item, so what happens in that case is my sub problem gets reduced to dp of I minus 1, j minus weight of j, plus the cost of I. So the cost of I is the answer that I'm getting in this case because I'm taking the ith item. So I'm incrementing my cost by this factor. And since I'm all saying that I have already chosen the ith item, so what happens in this case is the weight, like the maximum possible weight that I can carry, gets reduced down to j minus weight of I item. And my index of I shifts one to the left. And if I do not take the element at index I, so what happens is that I decide not to take this element I, so I have to decide on further elements, but the weight of my bag actually remains the same. And dp of ij, what dp of ij denotes? It denotes the maximum value taken till index I with current capacity as j. So these are the dp transitions. So we can write a recursive solution as well, like the initial states will be like I'm at the 0th index, like I have not chosen like any item before, and the total weight is w. So in this case, what will happen is, like since so what will happen is, like, I'll have a recursive solution that calls each of the other DP variables. So let's say I'm including the zeroth item. So my next DP state will be DP of first item and W minus weight of the zeroth item, and I will add to this state the answer for the zeroth item, like the cost of the zeroth item. So I can write a recursive solution in this case, and I can also write a iterative solution in this case. Let's say, how do we write the iterative solution? That is the bottom up solution. That is, we fill up all the DP values. So what we do is, basically we see that how many sub problems can we encounter. So let's say the weight of my bag is W and I have n items to choose. So the number of items can vary from, like the index of the item that I'm about to choose can vary from 0 to n minus 1, and the weight of the bag can vary from 0 to W, like the bag is completely filled and I cannot take any weight, like any more weight. So in that case, the weight of the bag will be reduced to W and will be reduced to 0, and this is the initial weight. So this can vary like this. So my 2D DP array looks somewhat like this. So these are, like, let's say, the weight variables from 0 to W, and these are the indices that I'm storing from 0 to n minus 1. So in the bottom up approach, what we do is, we basically try to store the answer for all the subproblems. So in this case, I'll see that if I do not, like, these are the number of items that I've chosen. So let's say n items. So in this case, I'll see that if I have a weight, if I have a bag with weight 0, so it doesn't matter which item am I on, I cannot take item. So what will happen is, the first column of the DP array will get stored to 0. And let's solve the problem for the weight of 1. So for the weight of 1, we can see that either we can store an item. So let's say the weight of the 0th item is 1 kgs. So in this case, if I have a bag of weight 1, so I can only take the 0th item. The rest of the items are heavy. So in this case, I cannot take those items anymore. So the cost of the 0th item, let's say, is 1 kg itself. So this will be the possible state, like up till n minus 1, like I can up from all the items. If I only have a weight of 1 kgs, I can achieve a maximum cost of 1 kg. So in this case, what we do is, basically we fill up all these DP values starting from lesser weight to a higher weight, and then to compute the this particular stage, we will just compute an answer that lies somewhat to the left of it, because we have already calculated the left values before. So I can directly take up the items, like take up the values in this case, and this will be my DP transition. So let's see how do we, like, implement this in the code. So as I told you, like, the base case, so let's define the dpij. So dpij initially contains some default value, so we are kind of initializing the array. So what will happen is, I said if there is no weight left in the bag, so it doesn't matter how many items, like I cannot choose any item, right? So in this case, for all the dp of I0, I assign a value of 0, because if the weight of the bag itself is 0 kg, I cannot choose any item. So in this case, my answer will be 0. And similarly, what I see is that no matter how much weight I can carry, let's say I can carry 100 kgs, let's say I can carry 1000 kgs, but if I do not choose any item at all, the answer would still remain 0, right? So in this case, I initialize my dp values as dp of 0 comma I is equal to 0, denoting that I'm not choosing any item, and no matter how much is the weight of my bag, my answer would still be remaining 0. And this is the main driver code for the DP. So I start iterating from the number of items from 1 to n, and I start iterating from the weight of the bag from 1 to W, because I've already defined the base cases for I equal to 0 and j equal to 0 right now. And I see whether I can include this item in the bag or not. So as we saw in the dice problem, so what happened in the dice problem was, like the answer for nth state was f of n minus 1 up till f of n minus 6. So somebody asked what happens in the case of f of 2. So in the case of f of 2, I cannot roll a die that shows me a number 3 in my last step, right? Because this is not a valid solution. Like I cannot roll a like I cannot roll a die that shows 3 and I can still get a sum of 2. So similarly, this happens in this case as well. So let's say the capacity of my bag is 10 kgs. So I cannot reduce it to a sub problem where I take an item worth 15 kgs and my sub problem gets reduced to I minus 1 and 10 minus 15, because if I have a bag that can at most carry 10 kgs, I cannot choose this item anyhow. Okay. So in this case, what I can only choose the item when the weight of the bag, like the carrying capacity of the bag, is greater than the weight of my item. So if the carrying capacity of the bag is greater than the weight of my item, so in that case, I have two choices whether I can choose this item or I cannot choose this item. So I take the maximum of both the possible answers. So what happens if I try to not take the item, so in that case what I'll have is dp of I minus 1 and j, because the carrying capacity of the bag remains the same. Otherwise, the cost increases because I'm stealing the ith item, but the weight of my bag is actually, like, the carrying capacity of the bag is actually reducing, and I'm transitioning to a previous state where I cannot choose the ith item. So since I said ki there are only one copy of each item, so I want to assure that I cannot steal this mobile phone twice. So in this case, I transition to a state of dp of I minus 1 because I cannot choose the ith item again. Otherwise, if I cannot choose the ith item, that is the carrying capacity of the bag is less than the weight of my ith item. So in that case, my dp would be just to ignore the ith item. So if I just ignore the ith item, so what happens is in this cases dp of ij just remains as dp of I minus 1 and j. So this is the implementation of this problem. So this was a bounded knapsack. So this problem is called the bounded knapsack. And let's move on to a similar kind of problem that is also very similar to this problem, but it has one additional one extra information in this problem. So this is called unbounded knapsack. So what happens in this case is the problem remains the same. Like the thief enters the mall that has n items, and each of the item has a weight and a value associated to it, and the bag can, like, the thief has a bag that can at most support one item. So what is the maximum amount that the thief can loot from this house? And note that we can take any number of items of one type from the mall. So since mall generally has multiple copies of each of the items, so suppose that the thief decides to steal this mobile phone. So in the mall you'll have multiple copies, like the showroom actually contains multiple copies of each of the items. So you can take any number of copies that you want. So this is the difference between the previous problem and this problem. So do you have like any suggestions or hint on how the problem statement will change from the previous problem? Like what is the difference between the previous problem and this problem? Like the how will the DP transitions change, to be specific? Anybody from the audience like wants to volunteer? I don't see any responses. Okay. That's fine. So what happens is, since I said in the previous case, the issue was कि if I take the ith item, let's say I take the ith item, so I cannot take the ith item again. And how did I implement this problem is that when considering the transition about dp of I comma j, I said that I'm talking about the ith item in particular, and I have a weight that has a carrying capacity of j. So if I try to include this ith item in my bag, so I was transitioning to a state of dp of I minus 1 and j minus the weight of the ith item. So I transitioned to a previous state where the number of items that were supposed to be chosen were from the range 1 to I minus 0 to I minus 1, because I said I cannot choose the ith item again. But what happens in this case is, since I have infinite number of copies of each of the item, I can still choose the ith item again. So let's see with the example that I said. So just a second. So in this case, let's talk about this example where just okay. So I said I have this problem, like where the weight of the item and the value of the item was 5 kgs, so it has a value of 5 rupees, and the other item had weight 4 as well as a value of 4, and I had 5 items each of weight 2 and a value of 2. So I said in this case, if I include my this item in my box, that is the item with a weight of 5, so I was reduced down to a sub problem where I have to decide between these items, and my carrying capacity gets reduced by 5 kgs. So initial weight that I was starting was 10 kgs, and my carrying capacity got reduced to 5 kgs. So this was the sub problem that I was remaining, and the maximum possible answer in this case was 9 rupees, because I can only fill up like I can only take 2 copies of these items, like this item and the other item, or I can choose this item worth 4 rupees. So in this case, the maximum answer that I could have taken was 9 kgs if I was only allowed to take each of the item once. So what happens if I am allowed to take each of the item twice? So in this case, this problem gets transitioned to other problem where I told that I'll choose the first item itself. I chose the first item itself. The weight of my bag got reduced down by 5 kgs. So this is the new weight that I'm allowed to carry. And but the problem says I can choose multiple copies of each item. So in the next step also, I am allowed to choose between all the possible items that were allowed before. So I can again choose this item worth value of 5, and I can achieve a maximum possible answer of 10 in this case as compared to 9 in the previous case. So if I choose if I choose this item worth 5 rupees. So this is how the problem statement changes. So the code essentially remains the same. Like this is the previous code. If you see the newer code, the code essentially remains the same, but the DP transitions would change. I'll show you the DP states for this. So what happens is, if I take the ith item, so my DP gets reduced down to a previous state where the cost increases because I'm including the ith item, but the transition takes place such that uh, I can still choose the ith item. So I move down to a DP value of DP of I and j minus weight of I, because j minus weight of 5, because I have chosen the item, so the carrying capacity of the bag actually reduced down. But since I can still choose the ith item again, so I do not transition to a DP state of I minus 1. As you see in the previous problem, the only difference was, if I was choosing the ith item, I was transitioning to a DP state of I minus 1 j minus weight of I. But in this case, since I can still choose the ith item again, so I transition to a state of DP of I comma j minus weight of I. And if I do not take the ith item, so in this case I transition to a DP state of DP of I minus 1 and j. So if you ask me why is this not DP of I comma j, so I'll tell you, like let's say let's say I have an item of weight 10 and a value of 7, and I have like multiple copies of this item. Like these are like I have the multiple copies of this item that are stacked in a shelf or something. So the thief actually went and stared at the first item. He calculated the DP variables in his mind, and he told, I'll not take this item. So if he decided to ignore this item, what like there is no point of taking the other item of the shelf. So since these are the identical items, so if we decided to ignore the first item itself, like there is a shelf that contains this all these items stacked. So if I'm talking about banana, so it will contain bananas, And if I talk about X, so the shelf will contain only X. So if the thief decided that I do not want to steal the X, if I do not want to steal the first egg itself, so what is the point of stealing the second egg? So once he decides to ignore the item, he completely ignores the shelf as well. So in this case, if we do not take the ith item, we transition to a state that is that doesn't contain the ith item as of now. Okay, so it doesn't mean that I'm not taking ith item at all. So let's say this is the shelf and it contains some X. So the thief decided to steal 2X. So it is like there are 5X in total. So the thief decided to steal 2X from the shelf, and he decided to ignore the third egg. So what I'm saying is, if he decided to ignore the third egg, there is no point of considering the fourth egg and the the fifth egg, because these are the identical items. And if I ignored the first item, like the third item itself, there is no point of moving on to the fourth and the fifth item. So this is what happens in this case. So if I do not take the ith item, what happens is I get reduced down to a problem of dp of I minus 1 and j. And the dp of ij convention remains the same. So dp of ij denotes the maximum value taken till index I with current capacity as j. So this was the knapsack problem, and this is the implementation of this. So if you see, the initialization remains the same. That is, if there is no weight left in the bag, so dp variable will be 0. And if I'm not taking any item, so the dp variable will again remain 0. And the dp states are also kind of similar, but the only difference is that if I'm taking the ith item into consideration, this dp of ij gets updated with dp of I comma j minus w of I, instead of dp of I minus 1 and j minus w of I. So this was the knapsack problem, and let's start with the problem solving session. So Saptarshi will discuss the first problem. So Saptarshi.
Yeah, before that, like we can give a 2 minute break to this
Yeah,
attendees
sure,
for, yeah.
sure.
So like you're giving, you can take a 2 minute break, and after that, we'll start with a couple of problems related to DP from code forces, and with that, we'll wind up today's session.
By the way, like if any of you had doubts regarding the previous content, you can ask us right now in the precast.
Okay, so yeah, let's start with the problems, DP problems, code forces. Let me share the screen. Yeah, I think my screen are visible, right?
Yes, it's visible.
Okay, cool. Yeah, so let's start with the Great Julia calendar. Let me open the problem. This is the problem. I want you all to, I'll give you 2 minutes. Here you guys can read the problem statement from here. So there are three sub-problems for this question. C1, C1 plus C2, C1 plus C2 plus C3. We'll do the first part today. C1, which for n less than or equal to 10 power 6. Yeah. I can also send you the link of this problem in the chat. So you guys can also access the problem on your own. Yeah. I can take 2 minutes to read the problem. Then I'll start. Okay, so I hope you read the problem. Let me explain you the problem. So the problem says that you have a number n, say n is like 347. Then in one step, what you can do, you can choose a digit from this number. Say you chose 4, you subtract 4 from it. So the number now becomes 343, right? So in this way, in one move, you can pick any number, any digit which is occurring in the number and subtract the digit from the number, and you go on till the number finally turns out to be 0. So you are being asked to find the minimum number of steps in which you can make any number n reduce to 0 using this particular moves. So anybody has any idea how we can approach this problem? Yeah, like obviously think in DP way. Like how we can use DP, like can take a minute or two, like think what will be DP of I in general, and for which we want to find the answer of DP of n. So what does DP of I represent, and how we can find DP of I using breaking down into various subproblems. Anyone has any idea? Okay, first tell me like what will DP of I represent? Anyone can tell me. This question is of DP, so I want to calculate the this
number of
question
steps required to make it 0.
make what
Minimum
0?
number of steps.
Minimum number of steps to make what 0?
347. The DP of the given number I.
What will I? Exactly. DP of I represents the minimum number of steps to reduce I to 0, right? So for any I, DP of I represents the number of steps to reduce I to 0, and we are given n. So finally, we want the answer. Our answer will be DP of n, right? Because DP of n will
DP of
represent.
I will be 1 plus DP of I minus.
Wait a second. Hold a second. Yeah. I'll come to that. I'll come to the recursion. Yeah. So DP of I represents DP of n will be a final answer, which will represent the number of ways to reduce n, which is given to us in the question, n to 0. Right. Now, how we will split this dp of I into various smaller subparts, and how we will merge them to solve dp of I. Yeah, now you can speak. Whoever was speaking. Hello. Yeah, someone was about to say their question.
I think my approach is wrong.
Oh, okay. No problem. No problem. No issue. Yeah. So, anyone else wants to give it a try?
dp of I will be 1 plus minimum of dp of I minus like number of digits taken one by one.
Exactly.
Like
yeah.
the digit taken one by one.
Perfect. Perfect. Yeah. So, say you have 347, right? You say you have 347, this number. So, what all can you subtract? I can subtract 3 from here to get 344. Or I can subtract 4 from here to get 343. Or I can subtract what? I can subtract 7 from here to get 337. Yeah. I can either subtract 3 or 4 or 7. So what are these? These are the distinct digits of this. These are the digits of this number, right? So dp, our answer will be dp of this. This will not be the sum of all this for this case. This will in fact be 1 plus the minimum of this. Because what is our question? Our question is the minimum number of steps to reduce n to 0. Our minimum number of steps to reduce 347 to 0, which will, when I subtract 3 or 7, I already consume one step, right? I've already consumed one step. So here I'm adding 1 plus when I consume one step, I can either get 344 or 343 or 337. So which step should I take? I should take that step which will eventually lead to me to the minimum number of steps, right? So say if this is minimum, I will take this path, right? If this finally gives to me the smallest number of steps, then I'll take this path. So all among these three, the minimum number, minimum dp of whatever all these numbers, minimum these plus 1 will give me the answer. Everyone got the logic? So the basic idea is dp of n is equal to 1 plus dp of dp of n minus digit of n for all digits of n. For all digits or all distant digits of n, it will be 1 plus minimum of it. Minimum for all dp of n minus digits of n. Is it clear to everyone? And what will be the base case? Base case will be like dp of 0 will be 0 and dp of single digit number will be 1 and so on. Like, yeah. So let's see the logic. Yeah, so the logic is that from number I having digits d1 to dk, we can see that we can either go to I minus d1, I minus d2, or I minus dk, right? These are the digits of the number I. So from I, we can go to I minus d1, I minus d2, or I minus dk. Now the minimum steps to reach 0 from I will be the minimum of these states plus 1, right? Plus 1 for the operation of subtracting from dj from I. dp of I denotes the minimum number of steps from I to reach 0. Yeah. So this is the code. So dp of 0 is 0, the base case. For I equals to 1 to n, this vector of digits I'm storing a vector of digits, and I'm for like this part of code does what? This part of code calculates dp of I. This entire part of code calculates dp of I using smaller subproblems which we have already calculated in the previous iterations of the for loop. Is it clear? Right. So this temp is I, like I'm stored this I in temp. Now what I am doing, this part of code while loop is storing the digits of the number I in a vector. So if it is 347 is my I is 347 now, the digits vector will store 3, 4, 7, right? Is it clear? Like digits of pushback 10% state and 10% slash equals 10 is standard, right? Now, after I store the digits in a vector, what I do is dpfi I initialize to infinity, like assume infinity to be already initialized to some very large number, 118 or something. I initialize dpfi to infinity. Now, this is the range-based for loop for the digits. I'm iterating through all the digits in the of the number. For all the digits, what I do is dpfi, I compare the current dp value with the dp of I minus digit. And if it is smaller, then I like update it. Like dpfi is minimum of dpfi comma dpfi minus digit. So is this part of the code clear? After this entire thing, I have finally calculated my dpfi is stored. dpfi is stored. And dpfi minus digit, it's already calculated in some previous iteration of the for loop. Right? Is it like, think of it as induction, right? So like induction, what we know, like for calculating the ith step, we already know the answer of from 0 to I minus 1. On knowing the answer of 0 to I minus 1, we are calculating the answer of I here, right? And we are going from till n. And after that, I output dp of n, which is my required answer. Anyone has any doubt? Again, so like, is it final time? Is it top down or bottom up? Hello, am I audible?
Bottom up.
Yeah, it's bottom up. Yeah, exactly. Like since we are going from 1 to n and storing, we're calculating dp of all the I from 1 to n. Yeah, it's bottom up. Okay, so this was the problem about this Julia and calendar. So great Julia calendar. So I don't think anyone is in doubt. So I'll hand over to Ashish, who will solve the next problem, vacations. Ashish, yeah, over to you.
Yeah, understood. Can you stop presenting? Okay, so let's move on to this problem, CF vacations. So I'll share the link of the problem in the chat as well, and you can read the problem through my screen as well. So just a second. I'll give you guys 2 minutes to read out the problem statement by yourself, and I'll discuss the problem statement over there. So in this problem, what happens is that there are n days of vacation, and Vasya knows the following information for each of the days. So like for each of the days, there can be like 4 events happening. Like out of 4 events, there can be one possibility that is happening. So one possibility is that on the day the gym is closed and the contest is not carried out, or on this day the gym is closed and the contest is carried out, or the gym is open and the contest is not carried out, or the gym is open and the contest is carried out. So uh, there is a gym and there is a contest. So each of them has the possibility of being open and of being not carried out. So these are the 4 events that can be happening. And Vasya, what she can do is she can either take a rest, or she can write the contest only if it is carried out on this particular day, or she can do sport if the gym is open on this particular day. And you have to find the minimum number of ways on which Vasya will take a rest. That is, she will not do any sports, or she will not write any contest. And the only limitation is that like she doesn't want to repeat any activity on 2 consecutive days. So she will not do sports on 2 consecutive days, and she cannot write contest on 2 consecutive days. So you have to find the minimum number of days that the Vasya will take a rest. And this information about what event is happening on each particular day is known to Vasya in the form of an integer array. So you have been given an integer array of length n, and it contains it contains several values from the range of 0 to 3. So if the value is 0, so it denotes that the gym is closed and the contest is also not carried out. And if the value is 1 in the array, so for this particular day, the gym is closed, but the contest is carried out. And if the value is 2, the gym is open and the contest is not carried out. And if the value is 3, the gym is open and the contest is also carried out. So this is the information that is presented to you, and you have to find the minimum number of days that Vasya will have a rest. So any possible suggestions to take this do this problem? You guys can take like 2 minutes of time so to think about the problem. Yep. So like the problem is you have been given an array of integer length n, and for each of the array elements it can be either 0, 1, 2 or 3. So 0, 1, 2 or 3. So and you have a person Vasya, and depending on the events that are happening across the day, she can choose to either take a rest. So Vasya has like three options: either take rest, or she can either do gym if the gym is open, and she can either give a contest if the contest is happening on that day. So she can like do only one particular activity on those days. So she can either rest, she can either do gym, or she can either do contest. And she wants to find out the minimum number of days that she can rest. So like for the minimum number of days, she wants to the other way that you can see this problem is you want to maximize the total number of total number of days that you are working. So since she is a workaholic person, she wants to maximize the total number of days that she is going to work. That is, she is either going to do gym or she is either going to do the contest. So what is a possible solution for this problem? So any hints, any suggestions? Like what can be the DP transitions in this case? Like what will be the DP states first of all? Like how can you determine a particular subproblem? So that is kind of simple to answer. So you can answer that. Like how do I define a subproblem? How do I identify a subproblem in this case? Anybody wants to answer?
DP of I can be like minimum number of days she took rest from day I to day n.
Okay. DP of I would be DP of I would be the minimum number of days she took rest from uh, up till from I to n. Yeah, from you can say from I to n or 0 to I. Like you can start the DP values from the back or the DP values from the front. That's fine. And like for each of the day, there is one more constant that you have been giving. So the constant was she doesn't want to do the same activity on 2 consecutive days. Uh, So if this constraint was not given to us, so what we could have just done is just made a transition of the on the DP values. So if, like the dice roll problem. So similar to the dice roll problem, what we'll have is we'll have a recurrence relation that says fn is equal to f of n minus 1 and f of n minus 2 up till so on. So similarly in this case, if this constraint was not given, so we can just have chosen that dp of I is equal to 1 plus dp of I minus 1 or something. Like she can just work all the possible days, and that would have been just simple. So since the problem requires that she cannot do an activity on two simultaneous days, so I cannot make a transition from dp of I to dp of I minus 1 directly, because let's say dp of I like denotes the maximum possible number of days that she can work. So I'm changing the problem slight a bit. So I have to find the minimum number of days that she took a rest. So instead of that, I'm solving a problem that is very same. Like I want to maximize the total number of working days. So in this case, let's say dp of I is the answer that the maximum possible working days up till the ith day. So I cannot directly make a transition to dp of I minus 1, because the thing is that I might have done gym in this particular day, and I'm also doing gym in this particular day as well. So I cannot make a direct transition. So only
You can send like two
yeah,
variables,
yeah,
like
what
I
would
comma the activity they did previous day.
yeah, perfect. So I have a DP state that says DP of I comma j. So this defines the answer for uh, up till day I when I am doing the jth activity on date I. Okay, so what I'm saying is like this is still the answer up till dp of I, but the last step that I took to reach this dp of I is the j. So what I mean is, if the value of j is 0, I took a rest. If the value of j is 1, I did gym, let's say. And if the value of j is 2, so j can have three possible states, because Vasya can do three possible activities. She can either rest, she can either gym, she can either do contest. So if this value of 2, then I did a contest on this particular day. So in this case, this clearly defines my subproblem, because if I want to transition from one DP state to the other DP state, so let's see how do we transition. So just a second. So suppose I said ki I want to do gym on the ith day. So I said this dp variable is 1. So in this case, this dp variable can come from dp of I minus 1 and 0. Like I took a rest on the previous day. And this can also come from dp of I minus 1, 2, but this cannot come from dp of I minus 1 and 1, because if I'm doing gym on ith day, I could not have done gym on I minus 1th day. So this is the only constraint that forces us to use a 2D DP. So this is how the DP variable will depend on the previous states. So can anybody of from the audience like can suggest a possible transition in this DP states? Like how will this DP of I comma 1 will get updated through this activity? So I'm saying that the DP of I comma j, like the DP of I comma j, it doesn't denote like the minimum number of rest days. It denotes the maximum possible working days. So you can do the minimum possible rest days as well, but that is not very intuitive. So let's define the problem as you want to work the maximum number of days. So let's say the dp of ij denotes the maximum possible number of days that you worked up till day I, and you did the jth activity on this particular day. So how will this dp of ij get updated? Anybody has any idea? Like I gave an example from this dp of I comma 1, and how this will get updated in this case is like, since I'm working on the ith day, so I chose gym. So in this case, since I chose gym, so it counts as a working day. So it will be 1 plus this dp of I minus 1 comma 0. and 1 plus dp of I minus 1 and 2, because since I'm working on ith day and this is the maximum possible answer for I minus 1th day. So I'll take the maximum of these two entries and this will be my answer. So how will it get updated in the case of dp of I comma 0? How will dp of I comma 0 be updated? Any ideas? Like, first of all, what did I say that this dp of I comma 0 denote? What does 0 denotes over here?
Rest.
Rest. So how will this dp of I0 get updated from the previous values?
0 plus maximum of 2.
What?
The
0 plus?
maximum
Acha,
of
Acha, maximum of the other two. But the thing is, like, you can rest on the particular days. So he does not want to do the same activity to consecutive day. It was not clearly mentioned. So it means he will not do sport on two consecutive day and write the contest on two consecutive day. So he can take rest on two consecutive days. So a DP of I0 is the only DP that gets updated through all the DP values. So DP of I0 will get updated by 0 plus the maximum of dp of I minus 1 0 and dp of I minus 1 1 and dp of I minus 1 2, because it doesn't depend on what you did on the previous day. You can always take a rest, but you do not want to do the same activity again. So I said this is the transition for dp of I comma 1. That is, if I'm doing gym on ith day, I could not have done gym the previous day. So the same transition follows for the case of the contest. So if I say that I want to update my dp variable dp of I comma 2, it gets updated as 1 plus the maximum of the other two entries. That is the dp of I comma I minus 1 comma 0 and the dp of I minus 1 comma 1. So this is how the dp value will get updated. And I want to find the maximum, like, okay, so my initial problem was to find the minimum number of rest days, and I transitioned that problem into maximum number of working days. So what will be the maximum number of working days? Like, what will be the answer for the maximum number of working days? Like, what will be the final answer? I have this DP array. What will be the final answer? What will be the values of I and j? So, any idea?
Maximum of DP of like 0 comma available options
Yeah,
on day
yeah.
0.
Okay. Yeah. Perfect. So maximum, it will be maximum of dp of, you said 0. Like, I'm not traversing from backward. I'm iterating on forward. Like, I'm doing a bottom up. So in this case, the answer will be maximum of dp of n minus 1 and 0. Uh, dp of n minus 1 and 1 and n minus 1 of 2. Also, like you mentioned one thing, key maximum of all the possible answers and all the possible states that can happen on that particular day. So I do not need to particularly take care about this, because what happens is, since I initialized my dp values by 0, so in this case, like, suppose on the n minus 1 day, let's say this is the array. So let's say the last index is the value at the last index is 0. That is, neither the contest happen on this day and neither does the gym open on this day. So in this case, since I have not updated this value, because I'll say that I'll only update this value if I have a contest or this going on. So this value will remain out to be 0. So this will indeed be the maximum possible answer in this case. So I do not have to do the case work in that case where I have to consider what is the activity happening on the n minus 1th day. Because if the activity cannot happen in this case, so you can see from the transitions that I do not particularly update the answers for this case. So this will remain out to be 0. So I'll show you my implementation of this problem. So this was basically the idea, and let's move on to implementation. So I take my input n, I take my input array, I define a dp variable dp of n plus 1 comma 3. So initially like I'm using a one based indexing for the array elements. So what happens is I'll initialize all of my dp elements to be 0, so that it doesn't so that I don't have to make this particular case work at the end. So what I do is I check whether the ith day, so since I have used one based index in this case, so this gets transformed into a of I minus 1. So I check what is happening on the ith day. So if the a of I minus 1 is equal to 0, that is neither the contest is carried out and also the gym is also closed. So what happens in this case? I can only update this particular value because I'll say that I can only rest on this particular day because I cannot do a contest when a contest is not happening. So I update only this particular dp variable, that is dp of I comma 0 is equal to maximum of dp of I minus 1 comma 0 and dp of I minus 1 comma 1, and it can take like for the previous day I am allowed to choose all the particular states. And what happens if a of I minus 1 is equal to 1? So in this case, the gym is open, but the contest is not happening. So I have an option to either take a rest or I have an option to either do gym. So if I take a rest, so the DP transitions remain the same as exactly as the previous state. Like if I choose to take a rest, so my previous day I could have taken a rest or I could have done gym or I could have done a contest. And if I decide to do the gym in this particular day, so my dp of I comma 1 will get updated as 1 plus the maximum of this comma like the dp of I minus 1 0 and dp of I minus 1 2. Similarly, if only the contest is happening on this particular day and the gym is closed, so I can either do a rest or I can either take the contest. So if I decide to take the contest, so what happens is my dp of I comma 2 gets updated as 1 plus maximum of dp of I minus 1 0 and dp of I minus 1 comma 1. And what if a of I minus 1 is equal to 3? So in that case, I am allowed to do all the particular three activities that I can either take a rest because the I'm allowed to take a rest at whatever time I want, and dp of I minus 1 also gets updated because the gym is open, so I can do a gym on that particular day, and dp of I comma 2 also gets updated because since the contest is happening, I can do a contest on this particular day. And so the answer for the maximum possible working days was maximum of dp of n minus 1 0, n minus 1 1 and n minus 1 2. So my initial problem was to find the minimum number of working days. So how do I find the answer for the minimum number of working days? So if I have the answer for the maximum possible number of working days, how do I find the answer for the minimum number of working days? Any anyone from the participants? Like I told, I analyzed the data over n days, and I told that the maximum possible working days was W. So what is the minimum possible rest days? Anyone?
N minus that number.
Yeah, n minus W, because if I'm working on W days, I have to take rest on n minus W days because this is what happens. If I'm not working, I'm taking a rest. So the minimum possible working days is the same as the maximum, like minimum possible rest days is equal to n minus like the total number of days minus the maximum possible working days. So this is what I do. I output n minus the maximum of dp of n comma 0, dp of n comma 1, and the dp of n comma 2. So this is the maximum possible working days, and if I subtract it by n, so it gives me the minimum possible rest days. So this is how I solve this problem. So any doubts on this problem, you can feel free to ask. I guess no doubts. I posted the link as well, so you can go over the problem in your free time as well, and you can submit the solution. We'll also be giving out a problem set on this DP, so you can solve that as well. And it will be containing the problems that can be solved by applying the techniques that are mentioned in this session. So yeah. Saptarshi, you want to hand over?
Yeah, okay, cool. Then, yeah, that was up from us regarding introduction to dynamic programming. I hope you enjoyed the session. After the session, we'll share with you the slides and the recording of the session also for those like who missed the session or attended partially. So the next session will be, I think it's on 12th December, a day after tomorrow, Monday. It will be on advanced dynamic programming. So we'll teach you about the advanced concepts in dynamic programming, and we hope we're looking forward for you to join the session also. Yeah, cool. Then that's it from us. If you have any doubts, you can stay back and ask, or else the session is over from us. You can leave. Thank you, everyone. Bye bye.
Thank you everyone for joining.